Hi there, this is James Claycomb from Houston Baptist University. Today I'm going to talk about biophysical simulations using QuickField software. And as just a basic outline, first we'll be discussing the relative size of cells for biophysical simulation. And it's important because cells are very small objects, and so we'll be using QuickField to be modeling objects that are on the order of microns in size with membrane thicknesses that can just be a few nanometers. First we'll look at a sample problem where I will set up the geometry. Then we'll look at the intrinsic membrane potentials in living cells and also model the charge distribution, the fields produced by charges in membranes. So, and in the second part of the talk we'll begin looking at induced membrane potentials when we put cells in external electric fields. And so we can modulate the plasma membrane and as well as organelle membranes, and also look at the frequency dependence of the membrane modulation. And this relates to bioimpedance simulations, where we're interested in the dielectric properties of living cells and tissues. And finally, I'll show some examples of calculating the dielectrophoresis forces, where we have electric field gradients. So the relative size scale of cells are very small. Cells are typically on the order of 50 microns in size, and this can vary significantly. However, the membranes consisting of a lipid bilayer, as I've illustrated here, are only about 7 nanometers in thickness. That means that our mesh density needs to span about 3 orders of magnitude in size. And if we look at this, this is just a screenshot of a model here, and I'm going to show you how to set this up. So what we're looking at is 1/4 of a cell, and this is modeled in axial symmetry, where the bottom axis here corresponds to the z-axis, and you can think about the cell being rotated about the z-axis here that's horizontal, pointing along the bottom of the page here with the positive z-axis to the right, and the radial coordinate moving up here. And in this problem, we have roughly 200,000 nodes, and we have in the regions away from the cell, this is a few hundred nodes, whereas near the cell membrane we have a few 100,000 nodes. So that's roughly 3 orders of magnitude difference in the size of each individual finite element here. So what I want to do is show you how to set this up in QuickField, and then we'll look at a few more examples. So what I'm going to do, I'm going to specify a new problem, and I'm just going to call this test cell. Okay, and I'm going to just leave this to be electrostatics for right now. We'll be doing simulations in electrostatics and also AC conduction. So I just, I'm going to choose Axis-symmetric because we have rotational symmetry about the model here, because we have a spherical, we'll try a spherical cell to begin with. Now in length units, I'm going to choose microns. Notice we can choose length units from microns, kilometers, miles. Some of these are useful if you're doing astrophysical simulations. Okay, so here's my coordinate system, and this axis is the positive z-axis moving out, and this is the radial coordinate as we're moving up. And you can see the coordinates on the bottom right-hand side in microns here. And what I'm going to do, I'm going to insert a circle here to define the boundary of my cell. So I just go to the Insert Shape tool, and I'm going to choose a circle, And now it's going to have a 50 micron diameter. And I'm going to position it where the central point is at the origin. So where I've highlighted the central point, this is the coordinates of that central point. And it doesn't, we don't need to rotate it by any amount here, so alpha is equal to 0. So I'm going to insert that, and it just appears as a little dot in the solution region. Now I'm going to create a second circle, which is going to define the outer boundary of the cell, and we need a separation of 7 nanometers between the middle circle and the outer circle. So if I type 50.007 microns, that'll give me a membrane thickness of 7 nanometers. So I'm going to insert this. Okay. And let's close this. So in order to see this, I need to zoom in here, and I can just go to full screen, zoom to fit. And this is these are the 2 circles that I've just drawn. And I'm going to zoom in. It doesn't look like 2 circles, but if we zoom in very close, you can see there is a separation between the 2. And this is an accurate aspect ratio of a living cell. So you can see that it's going to be quite some challenge having a mesh density that's fine enough to accurately model that. And I'll go back to the full screen mode. I need to put my solution region here, and as well I'm going to discard 3/4 of this circle here. So what I'm going to insert now is a rectangle, and now I'm going to position the bottom left-hand corner at the origin of coordinates because I'm just interested in the 1/4 of the cell. And I'm going to make the width of this 100 for right now, and we'll insert this. Okay, I'll close. Now it's intersected the cell here, and we're just interested in the first quadrant, so I'm going to discard the outer portions. I'm having to do this twice because there's two boundaries here. Let me delete this section here. I'll delete this. Okay, now I'll zoom to fit again, and this is our solution region. And I'm not going to mesh this one here, and we'll look at a different example. I just want to show you how to set this up. And if we're looking at an electrostatic calculation, I would apply a boundary condition, constant voltage here, and I would apply constant voltage here on this region. And I don't need to apply any boundary condition along the z-axis here, nor do I need to apply any boundary condition along the outer boundary of the cell. Okay. So if we go back to the, once I mesh this, it'll have an image like this, and it'll take a few minutes to solve. So we'll go ahead and solve some smaller problems in interest of time. One thing I want to look at is the membrane potential. Living cells have membrane potentials because there's ionic concentrations on either side of the lipid bilayer here. Typically, this membrane potential, or the difference in potential between the inner and outer surfaces, is on the order of millivolts. And it turns out that we have a millivolt potential difference across the cell membrane, whereas this is only a 7 nanometer thickness. That means that the electric field inside the membrane, the intrinsic electric field, is order 10 megavolts per meter, which is tremendous. So let's model this configuration. And I have a model set up already. I want to close this.